All right, in this video, I'll discuss several examples of net force calculations. Now, in this video, I'm specifically focusing on net force in the horizontal direction. I'm going to do a video about more complex examples when we have net force in the y direction as well. But in this problem, we're solving for the net force that would be required to give a mass of 56.44 kilograms and acceleration of 6.96 meters. I'll begin by drawing a diagram. So in this case, we have a box, we know the mass of the box, we know the acceleration of the box is 6.96 meters per second squared to the right, and so we're asked for the net force. In this case, I just drew two forces on this box. We don't even really care about the individual forces. I just want to know what is the net force, or the sum of all forces. So this problem is actually quite simple to solve. What's my relationship between the net force, mass, and acceleration? Right, this is Newton's second law. If I'm solving for the sum of the force, then I just have to plug in my mass and acceleration, and I'm done. So if I plug in my values and my units like so, I would get something like this. Then if I multiply out, I will get 393 newtons of net force, or the overall force to be required. Keeping in mind that, again, that a newton is a kilogram times a meter over a second squared. So in this case, I was asked for the net force, not in any individual force. So all I have to do is plug into Newton's second law, and I know what the sum of forces would be. If the problem went one step further and told me that we have a force of 100 newtons pointing to the left, and that the net force, in this case, was 393 newtons, then what I would know, right, is that this force would have to be 493 newtons. Now, again, the reason I know that is if I call this force A and this force B, right, the sum of the forces in the x direction in this problem is going to be equal to, right, A minus B. If I call left negative and I call right positive, then in this case that would mean that 393 is equal to A minus B. I also should point out that I know that I'm talking about the sum of forces in the x in this direction because in the y direction, we'll take a look at in a moment, my forces are balanced, and so I don't have any net force in the y direction. The box is not accelerating in that direction, so I don't have to look at it for right now. So that means then that B would be 100, so that would be 393 equals A minus 100, so then A would be 493 newtons. If I were asked, to go one step further and solve for an individual force given the net force. So that's just an example of how this problem can be made more complex. Okay, let's take a look at another example. Let's take a look at an example of a net force calculation involving kinematics. Let's say that you're stopped at a red light and you see the light turn green. You step on the gas, accelerating uniformly or constantly. If after 300 meters, your velocity is 30 meters per second, and if the net force on your car while you are accelerating was 700 newtons, what is the mass of your car? I'll begin by drawing a diagram and writing down all of my given information. All right, so I have my diagram, and I've labeled it with the information that I've been given in this problem, and I've identified the unknown that I'm solving for, which is the mass of the car. Now, I'll write down all of the relevant equations I have that involve the variables I've been given. So in this case, I'll write out my kinematic equations and Newton's second law. All right, based on these equations, which one has mass in it? Well, I see right here that the only equation that considers the mass of an object is Newton's second law. What two things would I need, though, to solve for the mass? Well, I would need to know the net force and the acceleration. Do I know the net force in this problem? I do. The net force is 700 newtons. But do I know the acceleration? I don't. So, what I'm going to have to do then is use one of my kinematic equations to solve for my acceleration. Which one would you use? Because we don't have time, using the first and third equation might be difficult. If we were to use the second equation, we see that we have all of the necessary information to solve for the acceleration. So our plan looks like this. We'll use that second equation to solve for A, and then plug in A and the net force we've been given to Newton's second law to solve for M. Let's do that now. I've written out my equation again on the left. I'm going to rearrange this equation for A before plugging in any numbers. All right, I went ahead and subtracted the VI squared to both sides and then divided by the coefficient of A. In this case, it was 2 delta x. I'll go ahead and plug in my values now. Plugging in values, I get that A, the acceleration of the car, is 1.5 meters per second squared to the right, or in the positive direction in this case. Now, I'll take that and my net force and solve for mass. I'll rearrange Newton's second law for mass first before plugging in. Plugging in my values, I get that the mass of the car is 1,050 kilograms, which is reasonable. So this is an example of how you can combine Newton's second law and kinematics to solve problems. Let's take a look at another example. Let's say instead of being given the net force, I was asked to calculate the net force. How would I go about doing that? Well, all you have to do is define a coordinate direction. So in this case, let's call right positive and left negative. And then I would assign any force pointing to the right to be positive and any force pointing to the left to be negative. I've gone ahead and drawn an interaction diagram for my scenario, and I'm going to draw a force diagram as well. So my force diagram for my cart would look something like this, right? The floor is pushing up on the cart, the earth is pulling down on the cart, the red team is pulling to the right, or the rope is actually pulling to the right, and the left rope is pulling to the left on the car. Notice that the left rope arrow is longer because I'm told that the magnitude in this case is 100 newtons, and the magnitude of the right force is 40 newtons. Now, in this case, I'm not needing to consider the forces in the y direction because I know, is the object accelerating? Is the cart accelerating in the y direction? No, it's not. So I know that all of my up forces must balance all my down forces. And in this case, I only have two. So I know this force must be equal to this force. So I'm not going to have a net force in the y direction. In other words, the sum of the forces in the y direction would be 0. That would be because my mass times A, right, this would be 0. So I don't need to consider the y direction. And we're going to take a look at the y direction a lot more in my next video. And if I were asked to solve for the net force in the x direction here, I would do something like this. The sum of the forces in the x direction would be equal to the force of the right rope on the cart minus the force on the left rope on the cart. I've gone ahead and just abbreviated that as FRR minus FLR, right rope minus left rope. In this case, I know that the magnitude of the right rope force is 40 newtons, and the magnitude of the left rope force is 100 newtons. Notice I didn't need to make the 100 negative. When we do our force diagram, we subtract all of the forces pointing in the negative direction, so they end up being negative and it works out. So that would give me a net force of negative 60 newtons, right? The sum of the forces would be negative 60 newtons. I could say in the x direction, but I know that I don't have a y direction net force, so it will just be the total net force in this case. So that would be negative 60 newtons, or 60 newtons to the left. Now, if I gave you the mass of the cart, you could solve for the acceleration of the cart and vice versa. So this is how you would go about solving for the net force if you're given multiple forces. All right, let's say that you're given an aerial view to the right here, so from above, of a box that's being pulled in 3 different directions by 3 different people. Someone's pulling on the box 300 newtons north, someone else is pulling on the box 100 newtons south, and then a third person is pulling the box 500 newtons at an angle of 30 degrees south of west. What would the net force on this object be? To solve this problem, we have to use vector addition to add all of the vectors in this case. Because we are dealing with an angled force, we're going to split that one into components and then use our vector addition skills, like before, to solve for the resultant vector, which in this case will be the net force, or sum of forces. I'll begin by making a table and labeling each of my force vectors. Now that I have my table and I've labeled my force vectors, I'll start thinking about the x and y component of each vector. For vector A, it is pointing directly north, and therefore has no x component. It is just a y component itself. That will be, x will be 0, and the y component will be 300 newtons, and that's a positive 300 newtons because it is pointing up. Now for vector C, we'll skip B for a moment. Vector C is pointing straight down, so it also has no x component. Its y component is negative 100 newtons, negative because it is pointing down or south. Now for vector B, we'll have to break vector B into components first. I can draw the components on the diagram to the right like so. If I were to solve for the magnitude of Bx using cosine of 30 and the hypotenuse, here 500 newtons, I would get an expression that looks like this. Similarly, for By, I would use sine and I would get an angle that looks like this. And I've gone ahead and approximated these in my calculator as well. I'll add Bx and By to my table now. And remember, They're both pointing left and down, right? Bx is left, by is down, so they both need to be negative. Be very careful about your negative signs here. If I add these all together, I will get the x and y component for r, my resultant force, like this. And if I draw out the triangle for my resultant vector, it would look like this. Then I can use the Pythagorean theorem to solve for r, the hypotenuse, and I will see that r is equal to 436 newtons. And if I were to solve for the direction, that would be my theta value inside of this triangle, I would use tangent inverse, right? Theta would be equal to tangent inverse of the opposite side, so in this case 50, divided by the adjacent side, 433.01, which would give me an angle of 6.6 degrees. And in this case, because this is west, and I'm going towards, right, this would be towards the south. South would be here. This would be an angle south of west, going towards south from west. So there you have it. An example of how you would solve for the net force if you're given multiple forces and you have angled forces as well. In this case, I didn't redraw my free body diagram because I was looking at an aerial view. This is a specific type of problem that I didn't feel the need to draw a force diagram for. So in this case, this is essentially a vector addition problem. Later, we'll deal with problems where it is incredibly important to redraw the force diagram with angled forces when we're looking at things from a side view. If I were to take this problem one step further then, and it said, hey, if the mass of the object is 10 kilograms, then what would its acceleration be, right? Well, that's no more difficult than taking the resultant vector that we solved for. We know that this is equal to the sum of the forces, right? This is equal to the net force. That resultant vector is the net force. So I could just take my Newton's second law equation, and to solve for A, I would divide both sides by the mass, and I would get that 436 newtons divided by 10 kilograms would give me 43.6 meters per second squared. So if I were asked for the magnitude of the acceleration, I would get that answer. Now, the direction would be the same direction, right? 6.6 degrees south of west. The acceleration and the net force will always have the same direction. And that's because the net force is what creates the acceleration. So they have to have the same direction. This concludes my video about examples with net force calculations. Please take a look at Canvas for additional practice problems to develop your skills even further.